A swimmer wants to cross a river from point A to point B as shown in the figure. The distance from A to C is 200 meters, and the distance from C to B is 150 meters, and the speed of the current in the river is 5 kilometers an hour. Suppose that the swimmer's velocity relative to the water makes an angle which is 45 degrees from the line as indicated. All right, couple things. I'm going to rename some of these things. The velocity of the water relative to the ground is 5 kilometers per hour, and it points that way. And the velocity of the swimmer with respect to the water, which is the thing that they want. All right, in the end, they ask for the speed of the swimmer relative to the water. What is their speed? In the problem as published, they call it U sub s, which I hate. So I'm going to call it VS SW, or is the velocity of the speed, the velocity of the swimmer relative to the water. And that is some unknown quantity, and it's at an angle of 45 degrees. And the thing they haven't talked about, but what we'll care about, is the velocity of the swimmer relative to the ground. That is also some unknown thing, and it's going to be at an angle, and that angle, which we're going to call phi, will be this angle. In other words, it's similar to the path it actually takes, because we know that the swimmer will actually move directly along that path. And that's going to be sort of our trick to all of this as we go on. All right, so one way to do this would be to set up the vector triangles and stuff. I'm going to do it a different way, an alternate way that I saw online. And I'm going to say, well, the horizontal part of the swimmer's motion relative to the ground, this bit, it's going to have a horizontal part, which I'll call just blah, and that's going to be minus the speed of the swimmer. Whoops, let's get colors nicely. It's going to be the velocity of the swimmer. Well, let's in fact look at it this way. It's really going to be how far the current carries it downstream. And then, but the swimmer is trying to go upstream, so we'll have something like this, where we've added them, but of course the swimmer is opposed. In other words, the water is trying to carry the person this way, but they're swimming up this way. And that whole thing, right, that velocity has to cover this distance, which is d2, in some amount of time, which we're going to call t. And then, likewise, the velocity of the swimmer relative in the vertical direction, well, the stream doesn't go in the vertical direction at all. It's just going horizontally. So it's going to be just the speed of the river. Although I should be careful here that these are each the x and y parts of them. All right? And then that has to equal, well, it has to equal this distance over the time. And it's going to be the same time for both of them. That's going to be our magic thing here. So let's try and plug in and see what happens. So I'm going to have to work in either kilometers or meters. I guess I'm going to choose to work in meters and then switch to kilometers later to actually get our final answer. It's not a big deal, but obviously a factor of 1,000 is sort of important. So we're going to have 5,000 minus the thing we're looking for, the speed of the swimmer versus relative to the water, times the sine of the angle. And that's going to give us d2, which I guess we know as well. d2 was 150 over t. And we're going to have that v sine over cosine theta is going to be 200 over t. And again, just like in the alternate solution we had before, we could do this by systems, which would be relatively nice and fast. But since that was the other method, let's just as an alternate here, I'm going to do it as algebraically, and let's see if that works out. By the way, of course, we know that cosine of theta is equal to sine of theta is equal to 1 over root 2 because of the 45 degrees, which just makes stuff magic. So rewriting this one more time, we'd have 5,000 minus 1 over root 2 times the thing I'm looking for is 150 over t, and also 1 over root 2 of the thing I'm looking for is 200 over t. And I'm going to take this equation and say instead then t is 200 root 2 over the thing I'm looking for. Going back up to the other equation, then we would have 5,000 minus 1 over root 2 times the thing I'm looking for is 150 over 200 root 2 over the thing I'm looking for, which gives us 150 over 200 root 2 times the desired unknown. And then, believe it or not, it really is just sort of ugly math, right? 150 over 200 is 3 over 4. So it's 3 over 4, 1 over root 2 times the thing I'm looking for. So, well, it's not particularly pretty, but we can do it. We bring that over and we get, let's change colors again, 5,000 equals 1 over root 2 times 3/4 plus 1 over root 2, all times the thing I'm looking for. So we can think of that as 1 over root 2 3/4 plus 1 times the thing I'm looking for. Simplify that one more step, so it's 1.75 over root 2 times the thing I'm looking for, and then I should just solve it over. The thing I'm looking for is 5,000 times root 2 over 1.75, and it'll be in meters per second. Grinding that out, we end up with 4,040.6 meters per second, which is really 4.041 kilometers per hour, which is the answer that Mastering Physics expected. So we end up in the right place.